So, hello everyone. Let's start today's lecture. So, I just hope my voice is audible. So, today is the 11th, today is the live problem solving session for the 11th week of the course Control System by Professor S. Shankar Ram. So in this course, in this week, mostly the Nyquist plots and the relative stability concepts had been discussed, and the assignments are related to those concepts only. So I will be discussing them. So the first question, coming to the first question says, uh, consider a unit negative feedback closed loop system whose open loop transfer function is given as this. Okay, so if we assume this as a block, like okay, so let me. So this is my system or plant. Just write it with another pen. This is my system or plant. This is my controller, and this is the feedback I'm giving, negative unity feedback, and this is some reference. Okay, and this is the output. Okay, so we'll and this whole system and the negative. So in the question, it says the G of S into H of S. It's given as the open loop transfer function is 2 into S plus 8 divided by S square plus 7S minus 8. So the first question says, what are the open loop poles? This is the open loop transfer function. So the open loop poles are clearly, we can see. We'll just equate the equation. Minus 8 is equal to 0. That means S minus 8, S plus 8 into S minus 1 is equal to 0. That means it's minus 8 and minus 1, plus 1. So we can clearly see this open loop transfer function. I'll use this open loop transfer function, like the open loop system is unstable. Why unstable? Because of the presence of the one open loop pole on the right hand side. Okay, it's a positive, it's on the right hand side of the S plane. That's why the system is unstable. Now next question says, what's the closed loop poles? So for the closed loop poles, what we have to do, we know the transfer function G of S H of S whole divided by 1 plus G of S H of S. So we will get 2 into S plus 8 whole divided by S square plus 7S minus 8 plus 2S plus 16. So this denominator will be S square plus 9S plus 8 is equal to 0. That means it's S plus 8 into S minus S plus 1 is equal to 0. So it will be minus 8 and minus 1. Now we can see when the open loop system was unstable due to the presence of the pole on the right hand side, the closed loop system is stable. Closed loop system is stable. Okay. So now the next question asks, what the next question asks? The next question asks is, From A and B, one can conclude that the mapped contour of the Nyquist in GSHS plane is the open loop, the n circles minus 1. Okay, now it asks about how many times uh, the it should encircle the GSHS Nyquist plot will encircle the minus 1 point, if whether it's in clockwise direction or in anti-clockwise direction. So I guess you have gone through the Nyquist plot, how to draw and those concepts, the mapping concepts, because if I will take all those concepts here, it will be very much hectic, okay, and I might not be able to solve it, okay, in the limited time. Okay, so uh, what we have the number of open loop poles on the RHS. We denote it as P, which is equal to, in our case, the open, it's 1. Okay, correct. Now, what is the number of open loop zeros on the right hand side? So what is the 0? We have the 0 as s plus 8. So s plus 8 is equal to 0. That means we have the 0 at s is equal to minus 8. So we don't have any 0 on the right hand side plane. That's why we can write s, it's z is equal to 0. So now we know the number of encirclements nc is equal to z minus p. For the system to be stable, for the number of encirclement it should have is nc is equal to z minus p, 0 minus 1, which is minus 1. That means the plot will have one encirclement around minus 1 comma 0 point in counterclockwise, because the number here is minus 1. If it had been 1, then it would be in clockwise direction, otherwise it's in counterclockwise direction. So this was a very fairly straightforward question. Okay, sorry. Okay. So we have the answer. There will be one encirclement in counterclockwise direction. Okay. So I guess this question was clear because it's a very fundamental question. Okay. Now coming to the second question. It's very similar to the first question. In the problem one. So what was the problem one? The open loop transfer function. Open loop transfer function was 2 into s plus 8 whole divided by s square plus 7s minus 8. Okay, so this was my transfer function, from which it says the planned transfer function is this one. So just remember the diagram I had drawn. According to the question, the planned transfer function, this is the planned transfer function, this is s square plus 7s minus 8, and considering unity negative feedback, okay, then what is the controller transfer function? Clearly the controller transfer function is s plus 8, because that's why the whole open loop transfer function is this one, then one can infer that the controller structure is that of, okay, the controller is S plus 8. Okay, so what is its form? So it's clearly, it's a PD controller. If you remember, the this was like, we had the structure for P controller, it's a constant. For D controller, it's S, and for I controller, it's 1 by S. For PD controller, it's kind of AS plus K. For PI controller, similarly, it's K plus, it's K plus 1 by S. So, uh, hello, am I audible, Hoysal? If you can just confirm. Okay, thank you very much. So actually, I have discussed two questions. So I'll come back to these questions after I finish the class. Okay. So uh, let's let's go through the third question. It's a very fairly straightforward question. I hope you have gone through the Nyquist plot, basics of drawing Nyquist plots. So the question says, LTI system who has open loop transfer function two poles in the right hand side of the complex plane. So from the question directly we have number of open loop poles on the right hand side is 2. That means the number P is equal to 2. Okay. Then what it says, with the remaining poles is in the left hand side of the complex plane. So for our Nyquist stability criteria, we do not concern about the poles, open loop poles, which lie in the left hand side of the complex plane. So from the plot of the open loop transfer functions contour corresponding to the Nyquist contour, corresponding negative feedback. Okay, so we have what more information? It's a unit negative feedback system. So why this is important? Because if this is the given unit negative feedback, then we can apply the Nyquist stability criterion, like the encirclement about -1. Okay, so what it says, the system is stable. The system is stable when -1 is encircled. How many times? In which direction? Okay. So in this question, it's given only the pole. Actually, the question itself is insufficient because this was the question which was given in the last year's assignment of the NPTEL course. So I have talked to the other TAs also. This kind of incomplete question. Here you have to assume the number of zeros on the right hand side because there is no information regarding that in the question, so you have to assume. Other so suppose assume the open loop zeros on the right hand side. So assuming this to be 0, the z will be 0, then the number of encirclement nc is equal to z minus p, which is 0 minus 2 is equal to -2. So what does the -2 encirclement means? Encirclement should be positive. So this means the encirclement will be 2, but it's in the counterclockwise direction. So there will be 2 encirclements in the counterclockwise direction. Okay. So I just want you to say, if this had been the case, the open loop 0 on the, like, if there is the, in the question it had been given 1, there is one open loop 0 on the right hand side, then Hoishal, can you just tell me what should be the encirclement, in which direction, if it had been 1, assuming 1. So using this formula, can you just quickly tell me or type in the chat how many encirclements about -1 and in which direction? It will be fairly straightforward. If it had been 1, then the Z would have been 1 and the NC will be Z minus P, which will be 0 minus, sorry, not 0, it will be 1 minus 2, which will be -1. That means one encirclement in the counterclockwise direction. Okay, so I hope this is clear. Should I go to the next question? Should I proceed to the next question, Haisal? Haisala? Okay. Okay. Okay, it's okay. Oh, it's okay. It's okay. So actually, the next question is kind of, it will brief about all the concepts in the frequency domain, like in uh, Nyquist and Bode. So even if you are catching up, I would request you to participate, like interact a little bit, like if you know the answers. Okay, so I will be asking very simple questions also sometimes. Okay, so the question says, the number of question number 4, it says consider a unit negative feedback closed loop system which open loop transfer function is given like this. Okay, so the open loop transfer function is given, one second, open loop transfer function is given as s plus 4 divided by s square plus 2s. Okay, so uh, first it asks about the gain crossover frequency, phase crossover frequency. That will go later. Can you just tell me what is the open loop 0 and open loop pole? If you can say the open loop, exactly, s is equal to -4. Uh, please look into it. What will be? It will be, one will be 0 and another will be -2. Okay. Then when we're analyzing the frequency domain analysis, in general, what we do is we take in normal control system sigma plus j omega. But as we are doing only frequency domain analysis, we are dealing with the pure frequencies. We'll take this as 0 and we'll take s is equal to j omega. So I can write my open loop transfer function s of j h of s is j, and replacing s with j omega, I can write my open loop transfer function is j omega plus 4 divided by j omega square plus 2 into j omega. Okay, yeah, correct. So can I write the uh, magnitude, like whenever we are considering a frequency domain analysis, we consider two things. One is the magnitude and another is the phase. Okay, into h of j omega. The magnitude will be simply the nominator magnitude. Can you just tell me what you, if you know how to get the magnitude and phase? Otherwise, I will just brief about it also. You know how to derive the, like, get the magnitude and the phase of a transfer function? Okay, okay. Just catch up, just simple catch up. Okay. You know this s plus j omega, this is in complex plane. So if this is a real axis and this is imaginary axis, so I can write s like j omega plus 4, like 4 in the real axis and 1 j omega in the 1 omega in the imaginary axis. Correct? Because j here is the uh, root of, negative root 1. Okay, so just tell me, you know Pythagoras theorem, that's very basic. If one some unit a unit is this and b unit is this, what will be the magnitude? With root over a square plus b square. Okay, yeah, this is the magnitude, and the phase is this value. Okay, you see this one, this is theta. So can you tell me theta, what is theta? Hmm, it's tan inverse b by a. Simple. Okay, so when we are dealing with this kind of expressions, this kind of looking menacing, but these are also simple. So here you can see in the numerator we have simple 4 unit in real axis, 1 omega unit in imaginary axis. So what will be the magnitude? The magnitude will be 4 square plus omega square root over. Okay, divided by the denominator. What is the denominator? I will just simplify the denominator. J omega plus 4 whole divided by minus omega square, because j square will be minus 1, plus 2 j omega. So I can write the denominator will be omega fourth plus 2 omega square, 2 omega whole square. Am I correct? This will be the magnitude. Okay, are you following now? Okay, yeah. And what will be the like the phase, the angle g of j omega will be into h of j omega. This will be simply, you know, the denominator tan inverse. What is the y-axis? Tan inverse omega by 4. Okay, and in denominator, in similarly in the denominator, what it will be, if you do like this is also correct. What tan inverse uh, minus, whenever it's in the denominator you need to subtract it, because the pole, it's kind of, we can write it as a plus ib, you know, we can write it as r e to the power I theta. So r is the magnitude and theta is the plot phase. So when it's r1 divided by r2 e to the power I theta 2, so they will be subtracted, okay, in ultimate. So this is just a brief. So you can write like this, j omega divided by minus omega square, but it's not advisable because through this you cannot solve the question actually. So what you will do, uh, here in the question, look at it, the question says s plus 4. I can take out s into s minus s plus 2. I can rewrite it like this in simple open loop pole kind of structure. S contributes direct negative 90 degree. Okay, because s is j omega, there is no real part. That means if you do plus 0, I can write. So the phase will be, phase of s will be tan inverse. Okay, I'll just erase this part. Tan inverse omega divided by 0, which is equal to 90 degree. Okay, everything you can derive. There is no need to remember or mug up anything in control system. So I can write from this expression 90 degree minus, and s minus 2 will give me tan inverse omega by 2. Is this clear? Now you can derive any given question, you can derive the magnitude and the phase, right? Yeah. Okay. Okay. So now the question says, what is the gain crossover frequency? So what does a gain crossover frequency means? Gain crossover frequency, I will write down the definition. Gain crossover frequency. This is the frequency, twice, the frequency at which the magnitude becomes 1. Okay, so that means the magnitude we had derived, g into h, which is, we had derived it as 4 square plus omega square root over whole divided by root over of omega fourth uh, plus 4 omega square. This will be 1. Okay, just a quick question. If the magnitude is 1 in normal scale, in dB scale, what it will be? In dB scale, yes, perfect, 0 dB. So this will, that means in when you draw in Bode plot, whenever the magnitude plot crosses this 0 dB line, if this is the 0 dB line, then that is the, that frequency is called the gain crossover frequency. Okay, so can you solve this? I'll just solve it. 4 square plus omega square is equal to omega to the power 4 plus 4 omega square. So I will get it as omega 4 plus 3 omega square minus 16 is equal to 0. That means omega square is equal to minus 3 plus or minus 9 plus 64 all divided by 2. This will come, I have the solution actually, so this will come around, one will be 2.772 or negative 5.772. So, but no, like it's like just we just do, we did na, like what we want, we are looking for the this frequency. This is the frequency at which the magnitude becomes 1. So that's why we require the omega at which frequency that becomes. So omega square can never be this minus 5. So this cannot happen. That means omega is equal to root over 2.772, which will be somewhere around 1.6649. I can write it as 1.665. Okay, this is radian. Never forget the unit. Okay, radian per second. This is gain crossover frequency. Understood how to derive the gain crossover frequency? Okay, so this solution is 1.665 radian per second. So what is the phase crossover frequency? The phase crossover frequency, similarly, phase crossover frequency, it's the frequency when the phase becomes minus 180 degree. Minus 180 degree. Okay, so what the phase we had derived? We had derived like tan inverse omega by 4 minus 90 degree minus tan inverse of omega by 2. This will be minus 180 degree. That means my tan inverse omega by 4 minus tan inverse omega by 2, this needs to be minus 90 degree. Okay. So for any positive omega, this can never happen. Okay, you can just verify by your side, like subtracting this 2 will never lead to minus 90 degree. So there is, I can write, there is no phase crossover frequency. So if it had been minus 60 or something, na, instead of minus 90 degree, if it had been minus 60, minus 30 or something like that, then we would have been deriving that. You need to remember this formula by your side. In 12th you had known tan inverse A plus tan inverse B formula, that you have to remember again and solve the question. So now for this question, uh, we doesn't exist. This does not exist. Okay. So next called, what is the phase margin and what is the gain margin? So what do you mean by phase margin and gain margin? Okay. So before giving you the this solution, I'll try to give you some insight. Suppose you are going on a road. Okay. This is the road and there is a cliff here. If you fall down, you will go to you are gonna hurt yourself or something like that. Okay. So one person is traveling on this and another person is traveling here. So whom can you say is on a safer side? They both are safe right now because they both are traveling on the good path, not but who is more prone to, like, if something happens, who will be more prone to going into the cliff, going out of the cliff, like jumping off the cliff? Can you answer this? This one or like this one, green one or blue one, if you can. The blue one, no, no. How? The blue one is more on the safe side, na? Because here is the cliff. If you fall down, you will die. So green is traveling on this here, and blue is traveling here. So green is more prone to getting into the uh, danger path, right? Similarly, in control system, if any pole lies on the right hand side, it's unstable. When it lies in the left hand side, it's stable. So one pole, the green pole, lies here, pole pair, and another blue pair lies here. So these two, this green plot, they are more prone to going into instability if something happens than the blue. So that means we can say they both are stable right now, but if something happens, if my system behaves a little abruptly, these two have more tendency to go into instability than this. So that is called relative stability. Blue has, we can say, the blue has more margin of error than the green one. So that is, there comes the margin. Margin is kind of two types. One is gain margin and another is phase margin. So gain margin is how much gain I can give into the system so that the system goes into instability. Okay. And phase is how much phase I can add to the system before it goes to the instability. So okay, I need to calculate gain margin and phase margin. So there is a direct formula actually. You have already calculated the gain crossover frequency and phase crossover frequency. So you just need to put for the phase margin, the formula is 180 degree plus whatever the phase you have got, okay, G of S, H of S, at the gain crossover frequency, WG. That means 180 degree plus tan inverse of omega by 4 minus 90 degree plus tan inverse omega divided by 2 at the gain crossover frequency omega g, which is 1.665. Okay, that means this will be 90 degree plus tan inverse what 1.665 by 4 minus this was minus tan inverse of 1.665 divided by 2. This ultimately will be 72.8 degree. Okay, so this was the answer. Remember, for phase margin we need the gain crossover frequency, and for gain margin we require the phase crossover frequency. It's like the opposite. Okay, so this is the like the gain at the phase crossover frequency. Okay, so as we know, the phase crossover frequency, the omega p doesn't exist, so the gain margin we can say is infinity. When that doesn't exist, that means no matter how much gain I give into the system, how much more input, constant input I give into the system will never go into instability. Okay, this is called the gain. So I'll just write the answers. So this is 72.8 degree and this is infinite. Okay, now the closed loop poles corresponding to the open loop transfer function given. Okay, this is very straightforward. The question I want you both, if you both can answer, this is a very straightforward question. If this is the open loop for unity feedback, S by 4 S square plus 2S plus S plus 4. So this will be S square plus 4. This is the closed loop transfer function. S square plus 3S plus 4. So what is the closed loop transfer, like closed loop poles? Can you just tell me quickly if you can derive? It's like S square plus 3S plus 4 equal to 0. You need to, then S is equal to minus 3 plus or minus 9 minus 16 divided by 2. So negative 1.5. Negative 1.5 plus or minus root over 7 minus 7 divided by 2. So I had the answers actually, so I'll write S1 comma S2 equal to minus 1.5 plus or minus 1.3j. Okay, so what does the question say? So it is 9.5 plus or minus 1.3j. So can you tell me if whether the closed loop system is stable or not? Saurav or Hoysala, anyone? Just looking at the poles, that's all you require actually. If the system is stable or not. Okay, this closed, okay, stable because all the poles are in the left hand side. Closed loop system is stable. Okay, consider, now the next question is, consider the closed loop sinusoidal transfer function given to the question 6. So low frequency value in dB. Okay, so we have the closed loop transfer function. Where is the closed loop? This. So we are told, like frequency domain analysis, we are giving sinusoidal to frequency. So for the frequency, what we need to do, we replace S with j omega. So when we replace s with j omega, what we get? It's minus omega square plus 4 whole divided by, oh my god, why it's square? So it's j omega plus 4 divided by omega square, negative omega square plus 3 j omega plus 4. Okay, I can write it as 4 plus j omega divided by 4 minus omega square plus 3 j omega. It's in real and imaginary part. So what's the question? I need to go back again and again. Okay, the low frequency, consider low frequency value magnitude. Okay, magnitude at low frequency. The next question says high frequency asymptote. Okay, yeah. So Hazel, can you just tell me what is the magnitude now? GH magnitude. You know how to derive it now. So can you just tell me so that I'll be yeah. Yes, divided by three omega whole square. Okay, very good. So now the question says, what is the magnitude in low frequency? So when we talk about like this, I don't know whether you have attended the previous classes where I had discussed the frequency domain analysis. In frequency domain analysis, what we do generally for two ranges. One is low frequency and another is high frequency. When we talk about low frequency, we mean really low frequency, like it's 0.001, 0.0001 omega, like that. And when we talk about high frequency means really high. Like, recently in India, 5G has been launched. 5G means what? 5 gigahertz band. 5 gigahertz means it's in 10 to the power 6, not 6, 9, 10 to the power 9. So it's really high frequency. So that's why when it's low frequency, when it's called low frequency, you can assume omega tends to 0, or omega is very much less than 1. Okay, so assuming omega is tends to 0, the magnitude will be in the low frequency, we can directly say it's root over of 4 square divided by what? Root over of 4 square. It's 1. In dB scale, it's 0 dB. Is it clear? When we talk about low frequency, that means we talk about really low frequency, which is omega tends to 0. That's why we just put 0 in omega and get the answer. So this question is solved. This is in dB, 0 dB. So next question says the slope in the dB per decade at high frequency asymptote. Okay, so now comes the high frequency band. So when we come to high frequency, the transfer function I need to write again, s plus 4 divided by s square plus 3s plus 4. Okay, so here we can see 1 0 and 2 poles. Okay. Always remember, in frequency domain, in dB scale analysis, zeros contribute to plus 20 dB per decade slope. Poles contribute to minus 20 dB per decade slope. So at high frequency, when there is there will be only high frequency range, so the zero will try to contribute plus 20 dB, and the pole will try to contribute. There are two poles, that's why it's negative 40 dB. Okay, so ultimately the Bode diagram, what you will have is like it's it was constant. The first uh, uh, just assume the first uh, zero appears, so it's plus 20 dB. Then it goes like this. Then what happens? Suddenly another the both the zeros happen, so it will be minus 20. Like from this, it's minus 40 dB. So that's why it will be contributed as minus 20 dB per decade. Okay, is it clear, or should I explain it again? Okay. Do you remember? I hope you had attended the last class where I had explained the drawing the Bode diagram. So, uh, you remember something like what I did? I for the first step of Bode diagram, the first step of Bode diagram is factorize it. Okay, I had repeatedly said this. Factorize it. Factorize into constant term, then zeros and poles. Okay. Suppose there are two poles now. Suppose the zero is at A, the poles suppose there are two poles. Okay, one at B, another is at C, omega. Okay, so till A, this is the frequency. Till A, the constant, there is some constant contribution for the magnitude plot. You remember? Then comes suppose A, A omega. Frequency is A. Then what will happen? Plus 20 dB per decade. It will be. It will go on, go on, go on, go on, go on. Okay, till it reaches B. At B, what will happen? B contributes to a pole minus 20. Minus 20 with respect to this. That means it was going at 20. Then you are making minus 20. Then what will happen? It will be 0 again. Okay. So from this, it will be like this. So it will try to go on forever like this. But then what happens? C happens. So when C will happen, what it will be? Again minus 20 dB it will contribute. So the final plot will be like this. It will go on forever for, with minus 20 dB. These are for simple poles. Okay, simple poles. Simple poles means S minus A, S minus B, and S minus C. Okay, but when in our system, it's kind of quadratic. So the concept remains same, but the diagram will be a little bit different. But this concept remains same. Okay, that's why it's minus 20 dB per decade. It's minus 20 dB per decade. So the last question of the day, corresponding to the question 6, the cutoff frequency of the closed loop. Okay. So the what is, first let's understand what is cutoff frequency. Why cutoff frequency? When we do the frequency domain analysis, cutoff frequency is the most important term like for you, because I don't know if you have used there used to be radio kind of systems where you need to tune the radio for FM going into different channels. Okay, so, and forget about radio. Have you ever heard about filters? Low pass filter, and what other filters you know? Low pass filter and very good band pass and all pass is been that is no filter. Another is high pass filter. So band block, anything. Okay, okay. So just imagine there is a low pass filter. So the low pass filter, how do you think the body diagram should look like? Low pass filter, what it does, it will pass the, okay, you told a very important term, the cutoff frequency. What do you mean by cutoff frequency? Can you tell me what do you, like you said till cutoff frequency? Hmm. Yeah, tell me what do you mean by little, the little? Okay, okay. Actually, like it's like uh, exactly you are correct. What it's the limit till which we want to pass, then we want to block everything. Correct? But practically, this is impossible to design a filter just like this or a high pass filter. If I want, I'll make exactly like this kind of discontinuous system. It's almost impossible. Almost what it is impossible. So practically, what you will get something like this. Okay. So at the cutoff frequency, there is a 3 dB drop always. Okay. And mathematically also you can derive it actually. The low pass filter, I'm telling you, control system is all about logic. S minus S plus A. So suppose at A, it's your cutoff frequency. So you can derive it like 1 by A, I'll 1 by S by A plus 1. Okay. Okay, I'll just because I'm telling you because it's a very beautiful concept. Okay, to factorize it, what I have told you first, s by 1 by s by a plus 1. This needs to be the plus 1 should be there to make our life easier. So cutoff at a. So what will happen? If the magnitude you have gone through the today's lecture, so tell me j omega by a plus 1. So what happens, like the magnitude, tell me the magnitude, it will be 1 divided by omega by a whole square plus 1. Okay, then cutoff cutoff frequency is a, so omega is equal to a. If we put omega is equal to a, what will be the magnitude? Exactly 1 by root 2. 1 by root 2. Okay, which is 0.708. In dB scale, this is 3 dB, negative 3 dB. You understood? Like that is why always at the cutoff frequencies there will be a 3 dB drop. Okay, so now the question is what the question says. The question says what is corresponding to the cutoff frequency of the. Okay, so what we want now, you can derive the magnitude, make the magnitude at which the magnitude will be 3 dB or 0.07. So we have the magnitude. What is the magnitude? The magnitude we have is 4 square plus omega square divided by 4 minus omega square root over is whole square plus 9 omega square root is equal to 708 or 1 by root 2. Make it 1 by root 2, it will be easier to calculate. Just make square 4 square plus omega square whole divided by 4 minus omega square whole square plus 9 omega square is equal to 1 by 2. Solve the omega, get the answer, the cutoff frequency. The answer will be somewhat around 2.13 radian per second. Understood why it's happening? The answer is 2. Okay, everything is clear. I hope you have understood this concept. Okay, so the first two questions were actually very basic. You can watch the video. I will upload it by tonight. It's very basic. The first question was there is a transfer function given, open loop pole you need to find, closed loop pole you need to find, and the Nyquist stability criteria, which I also explained in question number 2 and 3. Don't worry, just go through Nyquist lectures anywhere. You will understand this. This is the very basic concept. So that's all I had. So if you have some doubt, you can ask. Otherwise, I will close the class. Okay, thank you. So yeah, okay. So have a great week ahead. Thank you.